Welcome to all. This is lecture 4 on inverse trigonometric functions. Before we proceed, check out the solution of workout 4 that was given in my lecture 3. There are only 4 questions to be solved, and here it is. Now we proceed further. Let's discuss some basic concept on functions. Okay, what are the basic concept here? It is on composition of functions. Remember, if f is a function from x to y and g is a function from y to z, in such case we can have composition of exist, or we can have construct the composition of function, that is GOF. Okay, and remember this GOF function is from x to z. And what is x? X is the domain of f, and this z is the codomain of g. So remember, this GOF function is a function from domain of f to codomain of g. Okay, here you have the figure. If f is a function from x to y and y is a function from g is a function from y to z, we have composition of function, that is GOF is always a function from domain of f to codomain of g. Okay, so number 2, remember the function that is identity functions, and it is id subscript x. That means it is a function from x to x itself, and it behaves like it takes each element of that set to itself. Okay, suppose I have here a b c. Suppose here a b c, here also a b c. That means this function takes a to a, b to b, and c to c. Okay, the behavior of identity function is like this. It takes each element of that set to itself. Okay, now come to third one. Okay, given f is a bijective function from x to y, that means f inverse exists, and that f inverse is always from y to x. If f is from x to y, then definitely f inverse is from y to x. So now you have two functions, one is f and other is f inverse. Okay, so now we can have the composition, two types of composition. One is f composition f inverse, and other is f inverse composition f. Okay, now observe this one. F composition f inverse is a function from domain of f inverse to codomain of f. Okay, as I said, that GOF is domain of f to codomain of g. Similarly, it is from domain of f inverse to codomain of f. That is, domain of f inverse is y and codomain of f is y. So it is a function from y to y. Similarly, f inverse composition f is function from x to x. Okay, and what we are discussing here, we are taking that f is a bijective functions. Okay, now last concept here. Suppose we have a function from, it is from x to y. Okay, it's x to y. F takes small x to y, that means f of x is equal to y. Okay, or you can say that x is the pre-image of y, or you can write that x is equal to f inverse of y. Okay, so now what do we get? We get f composition f is a function from x to x. So suppose f composition f of x. Okay, it is f inverse of f of x. Remember, we have GOF of x is always g of f of x. Okay, so similarly, f inverse composition f of x is equal to f inverse of f of x. So which is equal to f inverse. What is f of x? F of x is y. What is f inverse of y? It is x. So what do we get? The f inverse of f of x is equal to x. Okay, we get here f inverse composition f of x is equal to x. In place of x, if you take x1, it is also x1. So what do we get? The behavior of f inverse composition f is exactly equal to identity function of x. Okay, that's why this is identity on x. Remember, f inverse composition f is the identity function on x because it takes each element of x to itself. Similarly, if you compose a composition f inverse, it is a function from y to y, and here I am taking this one. Which one? F composition of f inverse y. What is f inverse y? It is x. So what do we get? Y. So it takes y to y. F composition f inverse y is equal to y. This function behaves as identity function of y. So we can conclude f composition of f inverse of y is equal to identity on y. Okay. So based on this concept, we have this concept. What are these? The first one is, as you know that sine function is from minus pi by 2 close interval to minus 1 close intervals, and of course its inverse is from this to this. Then we have two functions here. One is sine, another is sine inverse. So we have two types of composition here. Of course, one is sine composition sine inverse, another is sine inverse composition sine. Remember the concept here. Okay, this is f composition f, another is f composition f inverse. This is f inverse composition f. Similarly, here we have sine composition sine inverse of x is equal to x. Okay, and remember this x, or we can say sine inverse cancel out. It is possible only when that x must belongs to the domain of sine inverse. Similarly, sine inverse sine will be cancelled out, or sine inverse of sine x is equal to x only when that x belongs to the domain of sine, that is minus pi by 2 close interval. Okay, this is the most important. We have sine inverse will be cancelled out only when that x belongs to the domain of sine inverse. Sine inverse sine will be cancelled out only when that x belongs to the domain of sine. Okay. Now one more things, we can say that sine inverse of sine alpha is equal to alpha always. It's not true always. Sine inverse of sine alpha is equal to alpha. It's not true always. It is true only when that alpha must belongs to the domain of sine, that is minus pi by 2 pi by 2. And remember what we are taking, we are discussing on the principal value branch. Okay. So similarly, here you have cos and cos inverse cancel out only when that x belongs to the domain of cos inverse, and cos inverse count cos will be cancelled out if that x belongs to the domain of cos. Okay. So similarly, you have for other trigonometric functions, you have it. Okay. Now come to the properties of inverse trigonometric functions. Okay. The first one is sine inverse of 1 by x. It will be cosec inverse x. Remember, it is written here x greater than 1 or x less than or equal to 1. What is written here? Just observe this one. This is x. Cosec inverse of x means that x must belongs to the domain of cosec inverse. And remember, the domain for cosec inverse is r difference minus 1 and 1 open interval. This is nothing but is x greater than 1 or x less than or equal to 1. Same things. These two represent same things. Okay. And remember, if this part is greater than 1 or less than minus 1, then definitely reciprocal is always in between minus 1 close interval. So whatever written here, it is belongs to the domain of sine inverse. Okay. So we have to prove it. Sine inverse of 1 by x is equal to cosec inverse x. How to prove it? You consider cosec inverse f x as y. So how do we get? If the cosec inverse part goes to right hand side, or that x is equal to cosec y, and the reciprocal of x, 1 by x is equal to reciprocal of cosec, it is sine. So how do we get? 1 by x is equal to 1 by cosec, here it is sine. So how do we get? That y is equal to sine inverse 1 by x. So from 1 and 2, how do we get? We get that. If y is equal to cosec inverse x, then y is equal to sine inverse 1 by x. So from 1 and 2 conclude that sine inverse 1 by x is equal to cosec inverse x. Okay, similarly you can prove this for cos inverse and tan inverse. Okay, now you try these problems. Okay, that the first one is solve the following, that sine inverse sine theta is equal to theta, and one other is sine of sine inverse x is equal to x. Okay, and remember, as you know these two things, similarly I don't need for all other functions, and you prove all this one. Cos inverse of 1 by x is equal to sec inverse x, and tan inverse 1 by x is equal to cot inverse x. Okay, and this is all about lecture 4. We'll proceed in lecture 5 further. Okay, thank you.